Greeting, Professor Dr. Somlat and everyone. My name is Pon Sukkitprasert. And today I'm going to present about a gas turbine engine. So we start with a gas turbine engine is a type of internal combustion engine that converts the chemical energy of fuel into mechanical energy through a continuous flow process. Unlike pistol engine, gas turbine operate steady with a on intermittent combustion cycle airflow continuously through the system, which allows smoother operation and high power output. The engine operates based on thermodynamic cycle because of its high power to weight ratio and reliability. Gas turbines are widely used in aircraft propulsion, large-scale power generation, and industrial application. So a gas turbine consists of five primary components. First is the inlet guides ambient air smoothly into the engine and ensure uniform flow into the compressor. Sorry, and the second, the compressor increase the air pressure significantly, sometimes up to the 20 or to the 40 times atmospheric pressure. In modern engines, this compression rise both pressure and temperature. Third, in the combustion chamber, fuel is injected and mixed with high pressure air producing high temperature gas. Fourth is the turbine extract energy from this gas to drive the compressor shaft. And finally, the exhaust nozzle accelerates the remaining gas to produce the thrust in aircraft engines or mechanical shaft power in power plants. So the gas turbine operate based on the open Breton cycle. First, undergoes isentropic compression in the compressor, increase its pressure and temperature. Second, combustion occurs at nearly constant pressure, where fuel is burned and the temperature rises dramatically. Third, the high energy gas expands to the turbine, producing useful work. The thermal efficiency of the Breton cycle increased with higher pressure ratio and higher turbine inlet temperature. However, increasing temperature introduces the material and emission challenges. Uh, in the combustion in gas turbine is continuous and occurs at nearly constant pressure. Compressed air enters the combustor and fuel is injected to the nozzle to create a stable frame. The frame temperature can reach between 1500 to 2000 Kelvin. The gas turbine operate under lean conditions mean excess air is supplied. Only a portion of the air supports combustion, while the remaining air is used for cooling and dilutions to reduce turbine inlet temperature. This uh, distribution is essential for protecting a turbine blades from thermal damage. Next, there is three main types of the combustor. First one is can annular and annular. Modern aircraft engines primarily use uh, an an annular combustor because they provide better temperature and uniformity and lower weight. A key design objective is to ensure uniform temperature distribution at the turbine inlet. And uneven temperature profile can cause thermal stasis and reduce turbine life. Additionally, the advanced linear cooling techniques such as a flame cooling are used to prevent the material failures under the extreme thermal loads. Despite its advantage, combustion in gas turbine present major engineering challenges. Extremely, we have extremely high temperature approach the melting point of turbine material, and frame stability must be maintained to avoid a blowout or flashback, and also the pressure loss inside the combustor must be minimized to preserve overall cycle efficiency. Most importantly, high combustion temperature significantly increase and NOx formation, creating environmental concerns. So, in gas turbine, the dominant mechanism is thermal NOx formation. So, when combustion temperature exceeds approximately 1800 Kelvin, nitrogen and oxygen molecules dissociate and react according to the uh, salvage mechanism. This makes NOx formation highly temperature dependent. Therefore, increasing turbine inlet temperature improve efficiency, but uh, simultaneously increased NOx emissions. So this trade-off is one of the most critical design challenges in the gas turbine combustion system. To reduce NOx emissions, modern gas turbines use several strategies. First one is lean premix combustion, lower frame temperature by operating with excess air. And next is uh, stage combustion, distribute fuel injection to better control temperature zones. The third one is water or stream injection, reduce peak temperature by absorbing heat. And the most advanced approach is dry low NOx technologies, which achieve low emission without water injection. So all these methods aim to reduce peak frame temperature while maintaining combustion stability and efficiency. Uh, Next is gas turbine offer high power to weight ratio, smooth, continuous operation, and high reliability. However, they face challenges such as high manufacturing costs, extreme operating temperature, and strict emission regulations. Additionally, the efficiency may drop at partial load conditions. Therefore, the engineering optimization is required to balance performance and environmental uh, compliance. So, in conclusion, gas turbine engines operate based on cycle and continuous combustion. Combustion temperature play as a central role in determining both efficiency and emission levels. While high temperature improve performance, it also increase NOx formation to thermal mechanism. A modern gas turbine design must carefully balance efficiency, material limitation, and emission regulation to achieve a sustainable operation. And thank you for your attention.